What up, mathletes? Whoop, whoop. All right, are you ready for this? Just move stuff around where I need it. Today's learning talk. Boom! Like magic. Or the power of pause on my part. I will identify and evaluate extrema and in behavior. Go ahead and write that down. Then I want you to take a look. We're going to use this graph right here to answer these questions. I'll give you a chance to do it. Ready, set, go. Again, pause it, do it, and then come back to this. So I'm just going to take a drink of coffee and start. Boom. All right. I'm assuming you did all that. According to Lifehacker, the graph illustrates the best time to arrive for a job interview. I can tell you from my experience, this is pretty accurate. According to the graph, what is the range of time that a person should arrive? Well, if we look right here, that best, like right here, is the pinnacle, right? This is the perfect range, which is, it's negative, which means early, right? Because this is minutes past schedule start, so that's when you should be here for your interview, when your interview starts. And this is how early, right? That looks like about, we're guessing, guys, these are 15-minute increments. I would say anywhere from, I don't know, 13 to 17 minutes early, if I'm guessing. If your guess is a little different, that's fine. So I would say around 13 to 17 minutes early. What happens to a person's chances of getting a job when they arrive too early? Well, they decrease. Why that is, I don't know. I'm sure there's some psychology thing. My experience is like texting too many times after a date, right? It's a little bit too needy. You know what I mean? You want somebody that's showing they're going to be there early. They're going to show up early before the schedule starts. They're ready for the day, but not so early that you're like, it's a little sketchy. What happens to a person's chances of getting the job when they arrive too late? Yeah, they go to zero. They go to zero. I mean, as you would expect, right? If you're not showing up for your interview on time, you ain't going to show up for the job on time. That's just a fact. How late could a person arrive and still get a chance of getting a job? I mean, if you look, there's just a little teeny area right there, like maybe 1 or 2 minutes. And it really doesn't matter the reason. Like, there's always reasons, right? And that's unfortunate, but it just is what it is. Describe the difference between arriving early and arriving late. Well, arriving early can increase your chances of getting a job. Arriving late gives almost no chance of getting a job. Boom. Look at that. I wrote it with you. How about that? Okay. Well, it's time to start the lesson. Again, pauses as needed. Write down what you need to write down. Let's roll with this. Sketching the graphs of functions. So I'm going to kind of use, where's something I can use? Yeah, boom, right here. Remember, we read it like we go left to right. What is this graph doing? Well, right here, to go left to right, it's increasing. And as it increases, we go all the way up here, and we get to a mountaintop, which is the relative max. And then what are we doing? Again, relative max right there, and then we're going. Now we start to decrease, right? So this one called out is decreasing. And then we get to a valley, right? The valley. I guess I should put mountaintop over here. Mountaintop. And we get to a valley, and we know that our valleys are what? They're a relative minimum. point right here. Okay? And then after our relative minimum, what happens again? Boom, it starts increasing again. And that's what you want to pay attention to, guys. If I ever give you the description that I'm increasing then decreasing, we know that right in between there's a relative maximum, right? Because it goes up to the mountaintop, then goes back down. But also if I'm decreasing and then I start increasing again, we know right at that point where the changes over is a valley. Okay. Let's take a look at this graph. In 2015, Christoph Strasser set a new 24-hour cycling record by riding 556 miles in a 24-hour period. The distance he rode over the 24 hours can be represented by a function. Sketch a graph that shows the distance y traveled as a function of time x. Well, important things we need to figure out here. 556 miles, 24-hour period. Okay? So if that's what happened, let's go to x equals 24, and then we're going to go up to, see this is 550, and it's just a little bit above that for 556. Now, at 0 hours, he had ridden 0 miles. So we just need to connect the graph on this. Boom. Look at that. And what does it say here? No distance has been traveled when he rode 0 hours. That's how we knew this. I forgot to read through this. Linear or nonlinear? The graph of the function is linear. It's funny because as I graph this, I'm like, well, how do we know he wasn't slowing down, stopping, and braking? Because it says it's linear. From time, it's positive from time greater than 0. So we know it should be in the positive. It's above the x-axis for time greater than 0. And in behavior, as the number of hours he has ridden increases, right, as it's going this way, the miles traveled increases. It's going up, which is the in behavior right here. Okay? Boom. That's how we graph it. Now we're going to use this information to help match a graph. I want you guys to take a minute, see if you can read all this, see if you can match to the information over here. I'm going to tell you the easiest ways to do that in just a minute. But ready, set, pause it, go. Okay, I'm assuming you did that. You know what I'm going to look at first, guys? Almost always in behavior. It says as x increases and decreases. So whether x is going left or right, the value of y is going up for both. I need to find that. Notice as x increases and decreases, the value of y is going down here, so that's gone. But then for all three of these, we see it's going up, going up, going up, going up, perfect, going up, going up. So we've already eliminated one. Okay? Now, let's look. It's positive for all values x. All right, all of these are positive for all values x. It's increasing for x is greater than 1. Okay? So let's look. That pretty much hits all of these. Oof. Oof. Uh-oh. Remember, I read these left to right. So if I look at this left to right, that means it should start going up for x is greater than 1. And notice this one going left to right, this one's still going down when I go left to right. So in this one right here, that can't work. But these two are still working, because if I put my pad right here, for x is greater than 1, it's increasing. Boom. For x is greater than 1, it's increasing. And this one, for x is less than 1, I see it going down, down to the valley. This one's going down, down to the valley. So these both still work, okay? The relative minimum is at 1, 4. So 1, 1, 2, 3, 4. That works. 1, 1, 2, 3, 4. This one still works. Ooh, it's still in the game. And it met the in behavior. The right half of the graph is a mirror image of the left half. Boom. Boom. Both B and D meet the criteria. Okay? All right. Some of this will take practice, guys. I know I'm kind of going through it because I'm used to it, but it will take practice for you. All right, let's look at this last one. Take a minute, read it on back. We're going to answer some questions about this graph. You should have your own paper. All right, it says in China, in 2011, China's urban population exceeded the rural population for the first time in the country's history. Use the description and graph to compare the urban and rural population of China from 2005 to 2014, where Y is the population in millions and X the years since 2005. So, even though it says 0, this really represents the year 2005. These are the years since 2005, right? And we see rural population. About 745,440,000 people lived in rural regions of China in 2005. Since then, the rural population of China has been steadily decreasing to 618,660,000 in 2014. Indicate true or false for the following statements. There were more people living in urban areas of China in 2005. Let's see. It says China's urban population exceeded the rural population for the first time in the country's history. Well, this would be false because it says their urban is increasing, right? Because the urban is actually overtaking the rural population, so that means it's increasing. The rural population of China, okay, this is the one that's been going down, right? It tells us has been decreasing while the urban population has been increasing. That's true because it says urban is going up, right? While the, dropping my pen here, it says the urban's been going up while the rural has been going down. So that's true. As the number of years since 2005 increases, boom, and we can see that, by the way. See this urban population that's going up, up, up? Shows us that in the graph. As the number of years since 2005 increases, the rural population of China decreases while the urban population increases. Yeah. So as the years increase, so it says the rural population of China has been decreasing while the urban increasing. So this is a little bit different as the number of years since 2005 increases. So this is increasing. What do we see? The rural population of China, this tells us it's decreasing right here, this information, while the urban population increases. Also true. It's basically the same as B, but it just uses the years now. The rural and urban population of China are positive for years after 2005 and negative for years before 2005. You can't have negative populations. It's not like you can have less than people, right? So it just does it. We're not looking at it. It's not that it's negative. It's just that it's less. Okay? So this is false. Both the rural and urban populations of China have been steadily decreasing. That's false. The rural is decreasing, but the urban is going up. False. Both rural and urban populations can be modeled by linear functions. Sure, that's true. Because we notice we can just do a steady decrease. We could do the rural by simply going, all right, starting at 2005 is 745 million, which would be about right here. And then to 2014, right? Over here, let's see, 6, 7, 8, 9, 10, 11, 12, 13, 14. 2014 is 618 million-ish, so it's going to be somewhere around in here, right? We could graph that, given the data. There we go, so that's true. Awesome, there we go. That's the lesson. With that said, peace out.